Every program you have ever seen follows rules a human wrote. Someone sat down, thought through every case, and typed out exactly what computers should do. If this, then that, step by step. Today, we built something different. A program that nobody writes the rules for. A program that looks at the examples and writes its own rules. Today, we find out how machines learn. For everything we've built in this series so far, the model has been same. You, the programmer, know the rules. You write them down as code. The computer follows them. Input goes in, your rules process it. Output comes out. This is traditional programming, and it has run the world for 70 years. But some problems break this model completely. Take a simple one, recognizing a cat in a photo. Try to write the rules. A cat has fur, but so does a dog. A cat has 4 legs. So does a tail, pointed ears, whiskers, a tail. Every rule you write has exceptions, and you'd need millions of rules to cover every angle, every lighting, every breed. It's impossible to write by hand. So, machine learning flips the whole thing around. Instead of giving computer rules, you give it examples, thousands of photos, each labeled cat or not cat, and you let the machine figure out the rules itself. Input and output go in, and the rules come out. That's the immersion. That's the entire idea behind machine learning. Read that again, because it's the most important sentence in this video. In traditional programming, humans write the rules. In machine learning, the machine discovers the rules from data. Everything else, every technique, every model, every breakthrough you heard about is just a method for doing that one thing well. So if the machine writes its own rules, what are those rules exactly? Where do they live? And what does it even mean for a machine to learn something? To answer that, we need to look inside the model itself. Here's the first thing to understand. A machine learning model is, at its core, a mathematical function. A box of full numbers, with knobs you can turn. Those knobs are called parameters, or weights. A small model might have 1,000 of them. A large language model, like the one you're talking to, has hundreds of billions. When the model takes an input, say, the pixels of a photo, it runs them through a chain of multiplications and additions, using those parameters, and produces an output, say, a number. That means cat or not cat. The exact values of those parameters determine what the answer comes out. Change the parameters, and you change the model's behavior entirely. So here is what learning means, precisely. At the start, all those parameters are random. The model is useless. It guesses. The learning is processes of adjusting those parameters, slowly over many examples, until the model produces correct outputs. That's it. Learning is just tuning numbers. Millions or billions of numbers, tuned until the math gives the right answer. This is why people say modern AI isn't programmed. It's trained. Nobody sets those billions of numbers by hand. That would be impossible. Instead, the numbers are discovered automatically, through a process we'll look at next. If you watch the loops video, this is going to feel familiar, because training a model is, at heart, a loop. The biggest, most important loop in all of computing. Let me walk through one pass of it. Step 1. The model makes a prediction. You feed it a training example. A photo it's never been told to answer to in this pass, and it runs the math with its current parameters and produces an output. Early on, this output is basically random. It might just say cat for a photo of a car. Step 2. Measure how wrong it was. We know the correct answer. The photo was labeled. So we compare the model's guess to the truth and calculate the error. In machine learning, this error has a name, the loss. A high loss means the model was very wrong. A loss that near zero means it nailed it. The entire goal of a training is to make the loss as small as possible. Step 3. And this is the clever part. Adjust the parameters to reduce the loss. The algorithm figures it out. For each parameter, which direction to nudge it, up or down, to make the error a little smaller. Then, it nudges every parameter, just slightly, in that direction. This is called gradient descent. And the nudging mechanism, the method that figures out which way to push each of the billions of parameters, is called backpropagation. Let me make the gradient descent intuitive. Imagine you're standing on a foggy hillside in the dark, trying to reach the lowest point in the valley. You can't see the bottom, but you can feel the slope under your feet. So you take a small step in the steepest downhill direction. Then you feel again, step again. Repeat enough times, and you reach the bottom. That's gradient descent. The hill is the error, and downhill is always toward a better model. Step 4. Repeat. Take the next example. Predict. Measure the loss. Adjust. Then the next. Then the next. Thousands of times. Millions of times. For a language model, this loop runs billions of times, often for weeks, across thousands of specialized chips. Each pass, the loss drops a little. Each pass, the parameters gets a little better, and slowly, invisibly, the model goes from random guessing to genuine competence. That is the engine of all modern AI. Predict, measure, adjust, repeat. A loop. Turning data into tuned parameters. Everything else is a detail on top of this. So far, I've been saying the model as if it's a box, so let's open it. The most important kind of model, the one behind almost every AI breakthrough of the last decade, is the neural network, and despite the intimidating name, the basic building block is simple. This is an artificial neuron, loosely inspired by the neurons in your brain. It does three things. First, it takes several inputs, each multiplied by a weight, one of those parameters we talked about. Second, it adds them all up. Third, it passes the sum through a small function called an activation, which decides whether the neuron fires, meaning whether it passes a strong signal forward or stays quiet. That's the whole neuron. Multiply, add, activate. One neuron alone can't do much. The power comes from connecting them, thousands, millions of them, into layers. The output of one layer becomes the input to the next. Data enters at the first layer, flows through the middle layers, and the result comes out at the end. And here's why the layers matter. Why this is called deep learning. Each layer learns to detect something more complex than the one before it. Show a network photos of faces, and the first layer might learn to detect simple edges. The next layer combines edges into shapes, a curve, a corner. The next combines shapes into features, an eye, a nose. The final layers combine features into whole concepts. This is a face, and it belongs to this person. Simple patterns built into complex understanding, layer by layer. That word, deep, just means many layers. A shallow network has one or two. A deep network has dozens, sometimes hundreds. More layers means the network can learn more abstract, more complex patterns. The depth is where the magic lives, and training that depth, adjusting the weights of every neuron in every layer using the loop we just saw, is what makes the whole thing work. So put it together. A neural network is layers of simple neurons. Each neuron multiplies, adds, and activates. The connections between them are weights, and training, gradient descent, running billions of times, tunes every one of those weights until the network as a whole can recognize a cat, translate a sentence, or predict the next word. Simple parts, staggering capability. That's the core trick of modern AI. Everything I've described so far, the photos labeled cat or not cat, is one style of learning. But there are three major kinds, and the difference comes down to one thing: what kind of data the machine learns from, and what feedback it gets. Understanding all three is what separates someone who's heard of machine learning from someone who actually understands it. The first and most common is supervised learning. This is the cat example. You give the model labeled data. Every example comes down with correct answer attached. A photo labeled cat, an email labeled spam, a house with its selling price. The model makes predictions, compares them to labels, and adjusts. It's called supervised because it's like learning with a teacher who marks every answer right or wrong. Supervised learning powers a huge share of AI you use: spam filters, medical image diagnosis, credit scoring, speech recognition. Anytime you have lots of examples with known correct answers, supervised learning is the tool. Its one limitation: you need labeled data, and labeling millions of examples by hand is expensive and slow. The second kind is unsupervised learning. Here, the data has no labels at all. You just hand the machine a giant pile of data and ask it to find structure on its own. No correct answers, no teacher. The model's job is to discover patterns, groupings, or hidden relationships that you didn't tell it about. The classic example is clustering, automatically grouping similar things together, a streaming service grouping viewers with similar taste, without anyone defining the groups in advance. A store discovering that customers who buy one product tend to buy another. The machine isn't told what the groups are, it finds them. Unsupervised learning is also how models learn to compress data, detect anomalies like fraud, and importantly, it's part how large language models first learn the structure of a language, by reading enormous amounts of text with no labels at all. The third kind is the most different, and in some ways the most fascinating: reinforcement learning. There's no fixed dataset of right answers. Instead, an agent, the learner, takes action in environment and gets feedback in the form of rewards or penalties. Do something good, get a reward. Do something bad, get a penalty. Over time, the agent learns a strategy that maximizes its total reward. It learns by trial and error, the way you would train a dog, or the way a child learns to ride a bike. Reinforcement learning is how machines learn to beat the world's best players at Go and chess, not by being told the best moves, but by playing millions of games against themselves and keeping what worked. It's how robots learn to walk, how systems learn to control power grids, and it's a key ingredient in making AI assistants helpful. A technique called reinforcement learning from human feedback, where the reward signal comes from humans rating which responses are better. So, three kinds. Supervised. Learn from the labeled examples with a teacher. Unsupervised. Find hidden patterns, no labels, no teachers. Reinforcement. Learn from a reward and punishment, by trial and error. Most real AI systems actually combine them. The model you're talking to right now was built using all three at different stages, but every one of them rests on the same foundation we built earlier. Parameters tuned by a loop to reduce error. So far, we've built up a general picture. A neural network is layers of neurons, and training tunes their weights with a loop until the network gets good at a task. That's the foundation. But there's a problem. The basic neural network we described has no good way to handle sequences, things where the order matters, and where each piece depends on the others. And the most important sequence of all for modern AI is language. Think about what understanding a sentence really requires. Take, the animal didn't cross the street because it was tired. What does it refer to? The animal or the street? Instantly, it's the animal, because animals get tired and streets don't. But to know that, you had to connect it back to a word earlier in the sentence, using meaning. A model reads words one at a time, in isolation. Can't do this well. It needs a way to let every word look at every other word and decide which ones matter. In 2007, a research paper introduced an architecture that solved this, and it's the reason modern AI exists. It's called Transformer. The T in GPT, in fact, stands for Transformer, and its key idea is a mechanism with a simple name: attention. Here's the intuition behind attention. When the model processes each word, it doesn't look at that word alone. It looks at every word in the sentence and asks, how relevant is each of you to understanding me right now? Words that matter get a high attention score. Words that don't get a low one. So, when the model processes its attention lets it focus strongly on animal and weakly on everything else. The model learns from data what to pay attention to using the exact same training loop we already covered. Attention isn't programmed by hand, it's learned. And here's why this was a revolution, not just an improvement. Older sequence models had to read word by word, in order, slow, and forgetful over long distances. Attention lets the model look at the entire sequence at once, in parallel, every word compared to every other word, simultaneously. This did two things. It made the training massively faster because you can process everything in parallel across thousands of chips, and it let models handle long-range context, connecting a word to something said paragraphs earlier. Faster training plus longer memory is exactly what unlocked models at the scale we have today. Now stack that. A transformer isn't one attention step. It's many attention layers stacked on top of each other, just like the deep networks we saw earlier. Early layers might learn basic grammar and which words to relate. Deeper layers build up to meaning, tone, intent, and reasoning. The same principle as the edge-to-face hierarchy from before, but for language. Stack enough of these layers, train them on enough text, and the model develops a starlightingly rich representation of how language and the ideas inside it fit together. So, how does this become ChatGPT? 3 stages. And notice that each one uses a kind of learning we already covered. Stage 1. Pre-training. The model reads an enormous amount of text, a large fraction of the internet, books, code, with one simple goal: predict the next word, over and over, billions of times. No labels needed. The text is its own answer key. That's unsupervised learning, at massive scale. This is where the model learns language itself. But a model that just predicts the next word isn't yet a helpful assistant. It's a very powerful autocomplete. So, stage 2, fine-tuning. We take that pre-trained model and train it further on carefully chosen examples of good question and answer behavior. Examples with the right responses attached. That's supervised learning, teaching the model the format and tone of being helpful, using labeled examples, exactly as we described earlier. And stage 3, reinforcement learning from human feedback, RLHF. Humans compare different responses the model gives and rate which ones are better. Those ratings become a reward signal, and the model adjusts to produce more of what people prefer. That's reinforcement learning, learning from reward, exactly the third kind we covered. This final stage is what makes a model feel aligned, helpful, and safe to talk to. Look at what just happened. To build the AI you talk every day, all 3 kinds of learning come together: unsupervised pre-training, supervised fine-tuning, and reinforcement from human feedback, running on a transformer which is layers of attention, which are tuned by same training loop, adjusting the same kind of parameters we start with. Every single concept in this video stacks into this one system. That's not a coincidence. That's the architecture of modern intelligence. Step back and look at what this series has built. We started at transistor, a switch on or off. We stacked switches into a CPU that follows instructions. We saw how memory holds those instructions, how operating system manages everything, and how a compiler turns human language into machine code. Every single layer, up to now, has been about one thing: a machine faithfully executing instructions a human wrote. This video is where that breaks. For the first time, the machine isn't following our rules. It's discovering its own. We didn't tell it what a cat looks like. We didn't write the logic for translating French or generating a sentence. We built a structure of tunable numbers, showed it data, and let a loop do the rest. That is a genuinely different kind of machine. Not a faster calculator, a system that learns. And that is how today's most powerful AI actually works. Not magic, not mystery. Parameters tuned by a loop, arranged into attention, stacked into a transformer, trained in 3 stages. Now you understand, genuinely, mechanically, what's happening inside the assistant you talk to. Most people never will. For 70 years, we told machines exactly what to do. Now, we show them examples and they figured out themselves. That is not a small step. That's actually a different kind of machine. And now you understand how it works underneath. Not the hype, the actual mechanism. If this gave you a new way to see intelligence itself, subscribe button keeps them coming. I'm Hex1000, Logic Behind the Code, signing out.